7番目は堀井澄香さんです。タイトルは Estimation of the Black Carbon Hastening Effect on Cryospheric Melting です。よろしくお願いします。
6127堀井澄香です。発表を始めます。Imagine you took a trip to the land of snow and ice, expecting to see a beautiful white scene, and instead, what you actually saw was this. Black particles covering the white surface of the ice. And this is what's actually happening in the Greenland ice sheets, Jakobshavn Glacier, the Antarctic, and the Arctic today. And what are these black particles? Well, these are called black carbon. Magnified, it looks like this and this. They're microparticles which consists of groups of microcarbon spheres, this tiny one, which ranging in size from 10 to 50 nanometers. And black carbon is less than 2.5 micrometers in diameter, which makes them what we call PM2.5. And I'm sure you have heard this before. And much like black asphalt on the sunny day, black carbon particles soak up the heat, whether they're in the surroundings, whether in the atmosphere or on the ground. And when they land on sea ice, a process called albedo feedback happens. These small dark particles settle on the surface of an ice, right here, of light-colored snow and ice, and they lower the reflection of light, or albedo, accelerating melting, and boosting sea-to-air heat transfer, and fueling global warming. This leads to the cycle of enormous loss of Earth's ice. And right here, over 88% of black carbon is produced in the Northern Hemisphere, specifically in Asian countries such as Malaysia or Indonesia or like other stuff. And by burning fossil fuels, they emit this soot or black carbon. And the most important fuel that they combust is coal, which is sektan in Japanese. So now what I've been working on the last few years is trying to visualize its effect on global warming, which is making some kind of formula to explain its contribution to global warming. And of course, thousands of other studies on this important factor of global warming have been done, and several simulations have too. However, as seen on the right, the majority only discusses the transportation and its distribution of black carbon, and only a few have ever researched black carbon itself's hastening effect. And therefore, that's why I'm doing this research. And creating a visualization of effect on black carbon is important so that we can push for more regulation on these black carbon emitting industries. And the reason why we have to nudge these people is because, for example, according to a climate science scholar, Miles Allen, he says, the fossil fuel industry knows how to stop global warming, but they're waiting for someone else to pay. Therefore, they don't want to stop it because they don't recognize how serious it is. And this just has to stop. So how do we do that? I started by asking two questions. One, how can we create a visualization to show the effect of black carbon on ice meltage? And two, by using the thing created in RQ1, how can we predict the speed of ice meltage in the poles actually? And what is, in effect, verifying RQ1? And my most straightforward idea to answer RQ1 was to recreate the scenario of the ice melting in nature, record it, and create a formula with black carbon as an explanatory variable and melting rate as an objective measure. And that's what I did. So first, I conducted my two experiments by one, tracing the mechanism of black carbon emissions caused by burning coal, and second, studying how these particles cause albedo feedback. First of all, synthesizing black carbon. Today, coal is the primary source of black carbon generation, but it's too difficult to obtain. So instead, I opted to use the pure benzene, which is the primary ingredient of coal, as listed right here. By combusting benzene in this experimental setup right here, we were able to catch and collect a sufficient amount of black carbon. But now, some may be wondering, is that really black carbon? How can you tell? Well, that's a great question. And let's all jump back to the definition of black carbon and check if it matches. So this is a micrograph. As we can see from this micrograph, they resemble the black carbon in structure. In addition, these two graphs indicates that they satisfy the condition of being less than 2.5 micrometers in diameter. Therefore, the particles collected in the first experiment can be said to be black carbon. And I can say with more confidence that we can conduct a second experiment much with more accuracy. So experiment 2. Okay, so now let's get back to recreation with black carbon in hand. I conducted second experiment tracing the mechanism of albedo feedback, which meant monitoring and comparing the melting speed of ice. And this number 1 shows the pure ice area, and number 2 is a black carbon covered area. And these were recreated on this scientific set that I made. Before sharing the results, I would like to define a variable, BC coverage. It indicates not only the BC accumulation on the surface of an ice, but also how much it was mixtured inside. And this shows the 10 trials that I did, the results of the black carbon covered ice's melting speed. And I want to conduct several analysis to make an estimation. So first what I did, with Python, I then ran a multiple regression analysis. This statistical technique analyzes the relationship between 2 or more variables and estimates the impact of targeting variable. And x1, x2, x3 represent for BC coverage, average humidity, and average temperature. But what does this formula mean? In order to check that out, I conducted several more analyses. The first was interpreting the formula by doing standardized partial regression analysis. Standardization is a process of putting different variables on the same effect so that we can compare its scale. Creating a visualization of effect was the second thing I did. This is a heat map. The heat map indicates the correlation between the two variables. The hotter the color, the stronger the correlation. And as we can see, as the results shown in the picture, the highest correlation was humidity and climate. And beforehand, it was temperature. Humidity had a strong correlation with the melting speed of ice. However, when we think of it, it is not what it seems. The rising melting speed of ice doesn't boost humidity, but this is not, doesn't boost humidity. And it is not true in the other way around. And needless to say about temperature and humidity. Humidity doesn't enhance temperature. And the cause and effect relationship cannot be reversed. Therefore, with humidity put aside, we can say that black carbon coverage is the most influential factor in the melting speed of ice. And that is what the formula tells us. Finally, I confirmed that the model prediction fits well with the evidence. I compared two values. A, the predicted value from the formula. As C, I put in some data. And B, the actual measurement of ice melting in Antarctica, which I gathered from JMA, Kishocho, and BBC. As shown in this graph, some data matches well. And I calculated the difference and the ratio. As shown, the ratio of A and B is close to each other. Therefore, the model can be said that it explains the data well, especially in some circumstances. In conclusion, we can roughly predict ice meltage in Antarctica by using this formula, which was created through recreations and simulation of the black carbon emission and also the albedo feedback. Still, further improvements can be made, and it is listed on the presentation. And this is a reference. This concludes my presentation. I hope some of what I presented seems interesting or even entertaining to some of you. If it was, I am truly grateful. Thank you.
ありがとうございました。それでは質疑応答に移ります。質問やコメントのある方は挙手をお願いします。質問は英語でも日本語でも構いません。前から2列目の方。
Thank you for your presentation. And I think in your experiment too, you have conducted a multiple linear regression to explain the melting speed. And I think you have used 3 variables. So why did you choose that variables as an explanation of melting speed?
Thank you for your question. My aim for RQ1 and experiment 2 was to create a formula in which black carbon coverage explains the melting speed of ice. And the first thing I thought when simulating some kind of phenomenon, I came up with using a multiple linear regression. But however, multiple linear regression requires you to have 2 or more variables to explain one targeting variable. And what I wanted to do was to put in some kind of variable which explains a condition in which black carbon was placed. Therefore, meaning like the how cold it is or how much humidity there is in Antarctica. And the most easiest data to gather from the internet about Antarctic and polar regions was humidity and temperature. Therefore, I put in these 2 variables in addition to the BC coverage and made my multiple linear regression analysis.
Thank you.
Thank you.
他に質問のある方は挙手をお願いします。右から1列目の。
Thank you for presentation. Can I speak Japanese? Okay.
Sure.
質問ありがとうございます。質問じゃない、発表ありがとうございます。溶けるスピードについての多分その式だと思うんですけど、溶けるスピードが多分そのアベレージテンペラチャーってところで多分マイナスになってて、多分気温が高くなると、溶けるスピードが落ちるって言ってると思ってて、それはなんか結構僕の直感に結構反してて、なんかあと BC カバレッジも多分上がれば上がるほど溶けるスピードが速くなるってことだから、まあでもそうか、そこはあんま疑問ではないんですけど、そのアベレージテンペラチャーがちょっと疑問なので、そのシステムについてちょっと教えてもらってもいいですか。
日本語英語日本語で答えさせていただくんですけれど、今回本実験が確かにその気温がマイナスになるのはおかしいなっていうのは自分も思っていて、なぜそうなったのかっていう考えると、ちょっとこれは今後の展望とかにつながる実験のちょっとした不備とかが含まれるんですけど、この実験が行われた時ってランプが入れられてるんですよね。右に見えるように。でそのランプって結構熱を放出する。でその熱を放出するのをほっといたら、この実験のセット、エクスペリメントセットアップの中身は完全に温度が上昇してしまうということなので、その気温の調整のためにちょっとマイナス気味に温度を設定しているんですね。でこの統計に使ったのはその平均のアベレージテンパチャーで、アベレージを取ったのは最初と最後の方で氷の、調べたかったのが氷が一つ溶けきるまでのスピードだったんですよね。なので、平均的なその最初から最後までの、気温の平均値をその重回帰分析に用いたんですけど、その時に実際にマイナスの値が含まれているのにかかわらず、なんか全部プラスとして扱われてたり、そういうこともあってマイナスになってしまっているのではないかと考えています。なので今後の展望としては実際にちょっと今回はリミテーションになってしまったんですが、あまりそういう気温の変化とかを気にせないでいいような、設備で実験を行うことを考えています。Thank you for your question.
Thank you.
時間の関係上、次で最後の質問とさせていただきます。質問のある方は挙手をお願いします。 そちらの前から3列目の方。
Thank you for your presentation, and I have a question about your definition of the black carbon. And in your study, and you focused on the black carbon from coal fuel, but there are so many other fossil fuel like oil or gas. So what is the reason of why you chose the coal fuel?
Thank you for your question. The reason why I used coal as the source of black carbon is because, as I indicated in this slide, most of the coals is emitted from the Asian countries. And as you can see in this slide, it's Japanese, but the most majority is actually from the Asian countries. And in these Asian countries, it's not fully developed, so they tend to use coal for their industries. And in addition to this, whether it was synthesized from coal or not, it's not that much important because black carbon is a particle which is combusted through the chemical impact through the carbon or the benzene that I use in this experiment, and also O2. So I believe that using benzene actually covers up the black carbon also emitted from other fuels such as gas or oil too. Thank you.
Thank you.
時間となりましたので以上で発表を終了します。ありがとうございました。